In this video we'll explore how Excel can help us understand the normal approximation to the binomial distribution using visual plots. This is a handy technique when dealing with large sample sizes, making calculations easier. The binomial distribution models events with two possible outcomes, like flipping a coin, repeated multiple times with a constant probability of success. To learn more about the binomial distribution itself, check out the link above. But what if we have a lot of flips? As the number of trials increases, this distribution begins to resemble the bell-shaped curve of the normal distribution. This allows us to use the normal distribution's properties for easier calculations. Let's create a simple table in Excel for the probability distribution of the binomial random variable. Let's say the random variable x follows a binomial distribution with parameters n equals 10 and p equals 0.8. We'll use Excel's binom.dist function to calculate the binomial probabilities for each possible value of x, which calculates the probability of a specific number of successes in a set number of trials, given a known probability of success and setting the cumulative argument to false to obtain the exact probability of each possible value of x. Now let's plot our data. We'll create the clustered columns to visualize the distribution. With a small sample size of 10, the binomial distribution is discrete and skewed to the left. Now, let's expand our sample size to 30, while maintaining the same probability of success. We will repeat the process of calculating binomial probabilities for each possible outcome within this larger sample using Excel's binom.dist function. When we visualize this distribution with a clustered column plot, we observe that the shape begins to resemble a bell curve. This observation emphasizes the fundamental principle in statistics known as the central limit theorem, which states that as the sample size increases, the binomial distribution converges towards the normal distribution, regardless of the underlying probability of success. By further expanding our sample size to 100, calculating the binomial probabilities for each potential outcome, and visualizing the results in a clustered column plot, we observe that the binomial distribution closely approximates a normal distribution. Next, we'll approximate the binomial distribution with a normal distribution by calculating the mean and standard deviation using the following formulas. To visually compare, we'll overlay the approximated normal curve onto our existing clustered column plot. This involves calculating the probability for each possible value of x, while applying a continuity correction to account for the transition from a discrete binomial to a continuous normal distribution. We'll use Excel's norm.dist function to obtain the cumulative probabilities for each value based on our calculated mean and standard deviation and setting the cumulative argument to true. For x equals 0, we calculate the cumulative probability of x less than equal to 0.5. For x equals 1 to 99, we calculate the probability of x falling within the range of x minus 0.5 to x plus 0.5, and for x equals 100, we calculate the cumulative probability greater than 99.5. To visualize this approximation, we'll copy the column containing the normal distribution probabilities and paste it into our existing clustered column plot, changing the chart type to a scatter plot with smooth lines. This allows us to directly compare the two distributions and observe how closely the normal distribution approximates the binomial distribution. By plotting the normal approximation alongside the binomial distribution, we visually confirm that when the probability of success is not too close to 0 or 1, the normal distribution effectively approximates the binomial distribution, particularly as the sample size increases.